Hello everybody and welcome back to another learning calculus video where this time around after we covered the chain rule we are now going to talk about implicit differentiation. And that sounds a little strange mostly because we haven't been calling anything differentiation except for whenever I would bring up the fact that dy dx or dx dt or something, anything with a d operator on there, is the differential form of writing a derivative. But implicit differentiation is its own monster. And I say monster, it's not really too crazy when you get into it. And I'm going to cover a really neat example that involves a circle of how to do this. And we'll be able to see how little bits and pieces work and split it up so that way we can really get in there and analyze what's happening as well as conceptually be able to see it. So let's get that started. And I have, again, like normal now, 3 questions that I'm going to try and look at through this video. And the first that we're going to talk about is what does it look like? And can we try it? And then what does it mean? What does it mean to implicitly differentiate something? Well, let's actually work our way up from the bottom this time, huh? That might be a little bit fun. So we'll start out with this. And we're going to kind of, actually, you know what? Let's mix it up. Let's start with this one, do this one next, and then we'll come back to can we try it, right? What does it mean? Well, up until this point, any equations that we've been given have been able to be explicitly differentiated or be able to take the derivative of it because it's already set up in the form of y equals and then the function of x. It's already set up that way. Y equals f of x. Like, for example, if we were to take y from our very first limit taking derivatives using limits video, if we were to take that, our x sine x, although I believe in that video is an x squared. However, in this video, we're going to use this. If we were to take this and look at this, we'd say, all right, well here's our f of x portion, because that is a function of x, and here's our y. So we can see that y is equal to f of x. And if we were to look at a different one that we kind of used before, square root of x cubed plus 1. If we were to look at that again, we have our f of x right here, and we have our y right there. So in general form, this remains true for explicit differentiation. But the problem with this is, let me ask you a question. What happens if we are given a formula? Let's put this scary equation in this nice friendly blue. What happens when we're given a formula of x squared plus y squared equals 25? I'm going to give you a minute to think about that for yourself. I'll allow you to pause the video, maybe try and come up with a way that you might be able to do this. And at this point, I'm going to assume that you have done so, and if not, that's fine. We're going to go through this together right now. In this case, what are we going to want to do here? Well, we want to take this implicit function, meaning that we don't have a y as a function of x formula yet, but if we solve to get it out to be y, we can then explicitly try to differentiate it. So let's start with that, right? Let's take this, and we have our x squared plus y squared equals 25. Well, let's go ahead and start with moving the y squared over, and we get x squared minus, let's flip to 25 as well, minus 25 equals negative y squared, okay? Flip the negative sign, right? Flip the negative sign so we get a positive y squared, so we have negative x squared plus 25 equals y squared. Bring that up here so we can continue. And we look at this again and we say, okay, well, what's the next step? First, now we got to eliminate the exponent. So we take the square root of it, and we'll just go ahead and reformat that entire equation to make it look a little bit cleaner. So now we have the square root of 25 minus x squared. Now let me ask you this. Have you caught the problem here? Have you caught the problem with this yet? If not, pause. Think about what I just did. And then, assuming that you've either figured it out by now or are ready to, we say, okay, we took the square root of something. Whenever you take the square root of something, you are left with two possibilities of what's under that radical. Because if this is squared, if this is squared, or if this is squared, or anything like that, there's a possibility that what was under the radical is either positive or negative. So therefore, we have to factor that in to our equation, so this becomes y equals plus or minus the square root of 25 minus x squared. And if we were to differentiate that, I'm going to save that for whenever we actually do go through and solve this. But we can take this actually and we can say, well, we can now look at graphically what that formula would look like, right? We haven't even done any derivations. But let's bring this down here and look at what this looks like. So let's take that. So we have y equals plus or minus square root of 25 minus x squared. It's a little bit of a bad 5. Let's just go ahead and get rid of that. 25 minus x. Well, that one's not much better, but it's all right. And let's say, okay, we'll graph it with the white to make it a little bit easier to make it the easiest to see on here. So we have this x-axis, and we have our y-axis. Okay? Knowing this, we can actually graph, or if you have a calculator, graph this out and visualize what this equation looks like, even though it was written implicitly as y being multiple functions of x. Because that's really, when you get down to the nitty gritty, that's what that y squared in the original equation was. That's what this y squared originally meant. Is basically saying there are two different y equations in here that we have to count. Which is why we ended up getting this right here. It's a little bit of an interesting way to think about it, but that's a way you can. So if we graph that, if we graph the positive, well, it's going to end up looking a little bit like this. Pardon if it's not perfect. I'm not great for freehanding semicircles or even... that's not bad. That is not bad at all. All right. So we have a semicircle whenever we graph the positive. So if we go ahead and do f of x equals positive square root of 25 minus x squared, we get that. And then a yellow, because they're complementary, we'll graph the other one. Well, if it's negative, you can pretty much just flip it over, and you get the same exact thing. Just upside down. So when you look at this, you say, okay, well, I just got a circle. Basically, once you graph the two equations together, the negative square root of 25 minus x, minus x squared. Once you graph these, you just end up making a circle. And I think that that's pretty neat. You can look at that and do the same thing for a lot of different equations. Let's actually look at another one that we as a I guess you could say class will not be able to differentiate in an effective amount of time because it's incredibly difficult. Nevertheless, is actually a little bit interesting because you can have a program do it. So let's go ahead and write out this equation. So if we have x cubed plus y cubed equaling 6xy. Now, this is actually I like it when equations have names because it means that they're interesting. This has a name it's called the folium of Descartes. and I'll show you what that looks like. But we aren't going to try to differentiate this ourselves, but we're going to look at what this equation is going to look like on a graph. And you'll see why it's incredibly difficult looking, and I'm actually going to graph because it, like I said, that y having that exponent of 3, you can basically infer that it's going to have 3 separate parts. And if I graph these parts for you, if I graph these parts for you in individual colors so we can kind of see, you'll sort of understand why it's not the easiest. Let me get this little bit right there. Okay, so that's the first part. The second part, if we look at it, if we're gonna do it, let's do this in purple. We have it going here. And then the third part we'll do in orange. You see what I'm saying now? That is going to be a nightmare to try and differentiate and find a formula that's going to do that. Stop here, loop back around, stop there, and then pick back up right there. That is atrocious. And that's why I'm thankful we have computers. But if we actually, now that we've seen a couple of graphs for this, if we go up here and take our x squared plus y squared equals 25 function, we're going to go down here and we'll actually solve it now. We'll actually solve that now. So we have x squared plus y squared equals 25. Now, let's think. What does it mean to implicitly differentiate something? Implicitly differentiating consists of differentiating both sides of an equation, both sides of the equation with respect to x, and then solving the resulting equation for y prime. Does that make sense? So let me go ahead and translate that into what I'm saying with this, okay? So if we take dy dx, right? Let's do dy dx. So we want to, well, here, we'll find dy dx. Yeah? Is everybody good with that? We'll find dy dx, which is essentially the equation of a tangent line. The slope, finding an equation that'll yield the slope of a tangent line. We already know all this. That is simple derivative things. But this time, we do it on both sides, and that's actually getting into the surface, grazing the top, grazing the top of the water of differential equations, which is an entire other course that requires a lot of thought and a lot of time. But here we can actually see a really neat way that this would go. So let's see here. We have ddx of x squared plus y squared equaling d dx of 25, right? Does that make sense? And I'm going to give you a second to pause and maybe try to get the next step and see, because I have a feeling that I know what might trip you up just a little bit. Okay, so let's continue. If we bring this down now, we then have d dx of x squared plus d dx of y squared equals 0. Because remember, the derivative of a constant is just 0, right? There's no variable. We can just assume that that's going to, well, we don't have to assume, actually. We know that it's going to be 0. And if we wanted to actually take it another step, it looks a little bit like a smiley face, but we could get 2x plus d dx of y squared equaling 0. And now this is where it gets tricky. This is why I put the chain rule before this, because like I said, it's building. All of this is building from here. Now we can see why we needed the chain rule in terms of this implicit differentiation. If we were to think of this as 2x plus d dx of f of x squared equaling 0, what is this? What is this? That is the chain rule, right? This is the chain rule. We have the function, because y needs to be, at some point, this is functions of x, right? So we technically have an x function inside of here, and then the y out here. So we can chain rule this, right? So let's think here. If we were to do that, and we'll break this off right here. So we're gonna take this right over here, and we're gonna do that in the white over here. We know that d dx of y squared is gonna be equal to dy I'm sorry, dy of y squared dy dx, right? Because the inside, outside, and then the inside, right? But the inside is just going to be a function of y still. So this is why it's kind of, in general, difficult, because you have to treat what's inside as a constant no matter what, and that whenever you take this derivative of the outside, the derivative of the inside will not change because it's already encapsulated with the derivative of the outside. And what I'm saying is, if you have y prime, you already have the derivative of everything that y prime is equal to. Does that make sense? That's saying if we have a derivative, a y being a derivative, then we know that the derivative of what it represents is already taken. Right? It actually is a little bit easier, but unfortunately doesn't work at any other point than now. So what I'm saying here again is that this will basically just come out to be 2y dy dx, 2y dy dx, because you still have to have that marker of taking the derivative of the inside with respect to x, because we don't have this in terms of x yet. We do not have that in terms of x. We know that it's in here, but we just have to figure out what it is, that way we can express it. So let's bring this back over. Let's bring this back over to here, right? So we now have this, and we know that this is equal. So 2x plus 2y dy dx equals 0. And it's important to remember that this is notation. This dy dx is notation. It is not an actual quotient that is equivalent to anything. It is notation. It's easy to think of these things as quotients that are equivalent, so that way we can just sort of say, okay, well, if we take this, we could split it in half and then take the derivative of that over there or something like that. And it makes it wrong because you can't actually do that. And this is when you realize, do I have the thought process for this? Am I able to clearly think, all right, this represents this, so it therefore in itself is also this other thing. That's where we're at right now. Now, if we continue down this path, it actually gets easier. This is the easiest part, honestly, because it's no longer conceptual. Now it's more of just, well, it is conceptual at all points, but now it's also just a lot of numbers. So let's think here. We have 2x plus 2y dy dx equaling 0, right? I just rewrote the same thing, but that's fine. What do we need to get rid of here? Well, if we're going to get this in terms of y prime, because that's what we're doing here, we need to find what dy dx is equal to. So let's do that. Let's subtract 2x, so that way 2y dy dx is equal to negative 2x. And then let's divide this side by 2y, so that way our dy dx will be separate. So we have dy dx is equal to negative x over y. Does that make sense? So if you actually remember, back at the beginning of this whole ordeal, was we were trying to find dy dx, which is exactly what we have just done. We have just found dy dx. We found it as negative x over y. But there's still a problem. If we wanted to find the equation of a tangent line at a certain point, well, what would we do? Well, if this function passes through a point, let's say it passes through the point of, what's a good one? We'll go with 3, 4. Go with 3, 4. Knowing this, and our dy dx is the slope of a tangent line, because that is what we have expressed several times across 8 videos thus far, that dy dx, the derivative, represents the slope of a tangent line when you solve for it, right? Dy dx f prime is the slope of a tangent line. Well, we have the slope of a tangent line now. We now know that if we were going to say, all right, well, Rm is equal to negative x over y, and Rx is equal to 3, and Ry is equal to 4, well then M is equal to negative 3 over 4, negative 3/4. Yeah? That's actually not too bad, is it? Now we can actually do some really cool stuff. Since we know our slope and we know our 2 points, these being the 2 points, the negative 3/4 being our slope, we can put this in slope-intercept form and find an equation. For where actually this thing is true, where this is an equation. So let's do that. So we have, if we were to put it in the form of y1 minus y2 equaling m x minus x2, that being an x1, we can put that in there. So let's do that. We can plug that in for y2 and plug that in for x2 and plug that in for m. So we have y1 being just y minus 4 equaling negative 3/4 times x minus 3. Let's bring that down again. Add our 4 over, so y equals negative 3/4 x minus 3 plus 4. Now if we distribute our negative 3/4, we get y equals negative 3x over 4 minus 3 over 4. I mean, not 3 over 4, minus 9 over 4. Minus 9 over 4. Plus 4. Well, we have a plus 4, so let's just go ahead and add that in to our 9/4, our negative 9/4, we should say. So then we get y equals negative 3x over 4. And then if we add in, so that's going to be 16/4 plus negative 9. So we subtract 9 from the 16 and we get plus 7/4. So there's our nice equation. There's our nice equation for the slope of the tangent line. I mean, an equation of the tangent line, I'm sorry. So if we were to draw that circle, if we were to draw that circle, or that, I guess that semicircle right here, if we were to draw that semicircle at the point of 3, 4, so let's say that was somewhere about here. That's somewhere about there. And we draw that tangent line right here. That is the equation for it. And now there's only one more thing. Well, we could write this in one other way. And that is 3x plus 4y equals 25. And hopefully that just straight up makes sense, because if we look back at our original equation of x squared plus y squared equaling 25, well, all we know is now that y and x are that, when we have our points, these are going to have to equal 25. All right, and that concludes this video, guys. I hope we all made it through that together. Implicit differentiation is probably one of the most difficult things to understand and to visualize and to comprehend at this point. Now, granted that it is calculus, it can only get, stranger from here. So, hopefully you stuck with it. And if you made it through, then congratulations. If you have any questions, please comment or message me or email me. Um, my email for this is begin learning. That is just a G. Begin learning calculus. Begin learning calculus at gmail.com. Email me at that if you've got a problem. Message me on Reddit. Just hit me up in any way that you can, and I'll help you out as much as I can. Thank you very much for watching. I'll see you all in the next one.